Hi class, here's the last video from chapter 4. We're still talking about moisture in the atmosphere, and this time we're going to focus on atmospheric stability. And what we're talking about with stability of air masses is, are those air masses rising, or are they tending to stay in the same position or tending to sink? And basically, if an air mass is rising, and rising on its own, that means there's nothing pushing it up. There's no mountain range that it's colliding with that's pushing it up. There's no wedge of colder air that's pushing it up. If an air mass rises on its own, then we consider it unstable. And that would be rises on its own because of its own buoyancy. If it tends to stay in the same position or wants to sink, then we would consider that stable. So we're going to look at three conditions of atmospheric stability: absolute stability, absolute instability, and conditional instability. So let's start with absolute stability. And the first thing we need to look at over here is the rate of change of temperature as we go up in the atmosphere. And this is the actual measured rate. So this would be if we took a weather balloon and we released it, and on that balloon we had a thermometer and we had a radio transmitter that was transmitting temperatures, and it had a GPS unit, so we knew the elevation. And so it's transmitting its GPS coordinates, its elevation, and its temperature, and we're able to record it as it goes up. And in this case, this example, the environmental lapse rate, or the rate at which the actual air temperature changes with elevation, is 5 degrees Celsius per 1,000 meters. So if we start at 20 degrees Celsius, we drop 5 degrees Celsius in the first 1,000 meters, another 5, and by the time we're at 5,000 meters in elevation, we're at minus 5 degrees Celsius. We can plot that on the graph over here. We have temperature on the x-axis, and so we start at 0 at the surface, and then as we go up in elevation, the temperature decreases. So that's our environmental lapse rate, the actual measured temperature in the atmosphere. Now, as an air mass rises, it cools adiabatically. And remember, we talked about adiabatic cooling. That happens because the air mass expands and the temperature decreases, just like letting air out of your bike tire, right? So that air mass, as it's going up, because pressure is decreasing, it's expanding, and it's cooling. And the rate at which unsaturated air, that's dry air, rises and cools is what we call the dry adiabatic rate. And that cools at a rate of 10 degrees Celsius per 1,000 meters. So notice over here, it's a steeper change in temperature with elevation than the environmental lapse rate. So the air is remaining cooler as it rises than the environmental lapse rate. So that means, cooler air is more dense than warmer air, so that air would actually want to sink. In this example, we have a wedge of cold air that's pushing that air up. So our air that's rising is colder than the surrounding air, and so it's stable. And so that's the key thing I want you guys to remember about stability, is really it's the temperature of the bubble of air that we're imagining rising compared with the temperature of the surrounding air that's going to determine its stability. If that air is cooler, then it's going to want to sink, and if the rising bubble of air is warmer, it's going to want to rise. So in this case, it wants to sink, so that's stable. So our rising air, in this case right here, it's 0 degrees Celsius because it's been cooling at a rate of 10 degrees Celsius per 1,000 meters. It's risen 2,000 meters, so it's cooled from 20 to 0. And it's actually 10 degrees cooler than the surrounding air. So that air mass, if we didn't have this cold air wedge here, would want to sink. But because we have this cold, dense air underneath it, it's pushing it up. And this is something we have fronts converge, and we're going to talk a lot more about fronts in a later chapter. Okay, so once that air mass hits that condensation level, remember the condensation level is where it reaches its saturation vapor pressure, its dew point temperature, then it rises at a different rate called the wet adiabatic rate. The wet adiabatic rate is a slower rate than the dry rate because of the presence of water vapor, and it ranges from 5 to 9 degrees Celsius. So in this case now, the wet adiabatic rate is 6 degrees Celsius per 1,000 meters. And the key thing is that the rising air mass, which is illustrated in this graph by the red line when it's dry and the blue line when it's moist, the rising air mass is always cooler than the surrounding air, which is illustrated by the purple line. And so that indicates atmospheric stability, absolute stability, because that rising air mass is being forced up, and if it weren't being forced up, it would sink. Okay? So let's look at our condition, and that is absolute instability. So again, here's our actual environmental lapse rate, and this time our environmental lapse rate is higher. It's 12 degrees Celsius per 1,000 meters. That means the air is cooling really rapidly as we go up. And now we'll look at our rising air mass, rising at the dry adiabatic rate and then the wet adiabatic rate, which are both lower rates than the environmental lapse rate. And so what happens now is, notice the temperatures here. So at 2,000 meters, our rising air mass is warmer than the surrounding atmosphere. And that's the same all the way up. So by the time we're up at 4,000 meters, our rising air mass is 8 degrees Celsius, and the surrounding air is minus 8 degrees Celsius. So if the air is warmer than the environment, then the tendency is going to be for that air to rise because it's less dense than the surrounding air. So this is an unstable condition, right? Because the air is going to rise on its own due to its own buoyancy, its own lower density than the surrounding air. It doesn't need anything to push it up. And so, for example, this is what's going on in a convective thunderstorm, right? With convective lifting. We have air that's heated by conduction from being in contact with the Earth's surface. It gets really hot. Because it's hot, it's less dense, and it rises just like so. In our graph over here, what we see is that our environmental lapse rate is showing the actual temperature of the surrounding air. And those temperatures are lower than the rising air mass. So the rising air mass is here in red and then in blue, and the surrounding atmosphere is in purple. And so our rising air mass is warmer than the surrounding air, and so it's unstable, and so it's going to go up. Okay, so a little bit trickier one is what we call conditional stability, and this is actually the most common type of atmospheric stability. This happens when the moist air has an environmental lapse rate between the dry and wet adiabatic rate. So what we have going on down here, our air mass is stable, because if it weren't being pushed up, it would fall. Then it gets to a point where it's actually warmer than the surrounding air, and then it is unstable. And so and doesn't need to be lifted up. So if we look at the graphs, so that environmental lapse rate is actually a rate that's between the wet rate and the dry rate. So in this case, our environmental lapse rate is 9 degrees Celsius, our dry rate is 10, our wet rate is 6, and so 9 is between 6 and 10, and so we call this conditional instability, and this is also very common. Now, instability is typically what's going to create some storms. That's what's going to create our more extreme weather. When we have stable conditions, we aren't going to see, you can get precipitation, but it's not going to be the kind of precipitation that you get when you have instability.